Hi there. In this video, we're going to be talking about oscillators and how they work. An oscillator is a circuit that generates a continuous waveform, such as a sine wave or a square wave. These waveforms can be used for a variety of purposes, such as generating radio frequencies for communication or creating sound waves for audio applications. There are several different types of oscillators, each with their own unique characteristics and applications. Some common types include the LC oscillator, the RC oscillator, and the crystal oscillator. The basic operating principle of an oscillator is based on the concept of positive feedback. This means that a small portion of the output signal is fed back into the input, causing the circuit to amplify the signal and generate a continuous periodic waveform. Common output waveforms are the sine wave, square wave, and sawtooth. There are several different types of oscillators, each with their own unique characteristics and applications. Two main types of oscillators are feedback oscillators and relaxation oscillators. Feedback oscillators are electronic circuits that generate a continuous waveform by using the principle of positive feedback. Positive feedback is a phenomenon that occurs when a portion of the output signal is fed back into the input, resulting in an amplification of the original signal. This process repeats itself, causing the circuit to oscillate and generate a continuous waveform. The key component in a feedback oscillator is an amplifier, which amplifies the input signal and generates an output signal. The output signal is then fed back into the input through a feedback loop, which includes a phase shifter and a frequency determining element. If the amplifier is a non-inverting type, the feedback circuit does not invert the amplifier's output, producing positive feedback. But if the amplifier is an inverting type, the feedback circuit inverts the amplifier's output, again producing positive feedback. We can see how the signal presented in the figure. In summary, feedback oscillators rely on the principle of positive feedback to generate a continuous waveform. This phenomenon is called oscillation. Two conditions are required for a sustained state of oscillations. 1. The phase shift around the feedback loop must be effectively 0 degree. The feedback circuit accomplishes the necessary phase shift according to type of amplifier used. 2. The closed loop voltage gain, a CL, must be than 1. For a sine wave oscillator, shown, the closed loop gain equals exactly 1. Otherwise, the output is distorted with clipping. The voltage gain around the closed feedback loop ACL is the product of the amplifier gain AV and the attenuation B of the feedback circuit. As CL equals AV times B equals 1. For example, what is the gain required for the amplifier portion of a sine wave oscillator if the feedback fraction, B, is 0.05? By using the formula for closed loop voltage gain, as CL is equal to AVB. So AV is 1 over 0.05. So, the gain required is 20. Feedback oscillators are electronic circuits that generate a continuous waveform by using the principle of positive feedback. Positive feedback is a phenomenon that occurs when a portion of the output signal is fed back into the input, resulting in an amplification of the original signal. This process repeats itself, causing the circuit to oscillate and generate a continuous waveform. Feedback oscillators require a small disturbance such as that generated by thermal noise to start oscillations. This initial voltage starts the feedback process and oscillations. For oscillation to begin, the voltage gain around the positive feedback loop must be greater than 1 so that the amplitude of the output can build up to a desired level. The gain must be then decreased to 1 to maintain the correct level of output without distortion. The voltage gain conditions for both starting and sustaining oscillation are illustrated in following figure. In computer simulations such as multi-sim, due to usage of digital signal which do not have thermal noise, this often create a problem when a computer trying to do simulations of oscillators. We will investigate this later when discussing about phase shift oscillator. Three types of feedback oscillators that use RC circuits to produce sinusoidal outputs are the Wien bridge oscillator, the phase shift oscillator, and the twin-T oscillator. RC feedback is used in various lower frequency sine wave up to about 1 MHz. The basic circuit of a Wien bridge oscillator consists of an amplifier, 2 resistors and 2 capacitors connected in a feedback loop. The feedback circuit in a Wien bridge uses a lead lag circuit. R1 and C1 together form the lag portion of the circuit, R2 and C2 form the lead portion. The operation of this lead-lag circuit is as follows. At lower frequencies, the lead circuit dominates due to the high reactance of C2. As the frequency increase, XC2 decreases, thus allowing the output voltage to increase. At some specified frequency, the response of the lag circuit take over, and the decreasing value of XC1 causes the output voltage to decrease. The response curve for the lead lag circuit shown indicates that the output voltage peaks at a frequency called the resonant frequency, FR. When the R's and C's have equal values, the output will be 1/3 of the input at only one frequency, and the phase shift at this frequency will be 0 degree. The basic circuit of lead lag is used in the positive feedback loop of an op-amp as shown in the figure. Notice there is a voltage divider is used in the negative feedback loop. As you know, for the circuit to produce a sustained sinusoidal output, oscillate, the gain around the loop must equal unity or 1. Because the Wien bridge lead-lag feedback network attenuates the output by 1/3 with equal R's and C's, the gain of the non-inverting amplifier must be exactly 3.0 to produce a loop gain of 1.0. The gain is set by R1 and R2. If the gain is too little, oscillations will not occur. If it is too much, the sine wave will be clipped. In the basic circuit shown, it is nearly impossible to set this gain to the precise value required for non-inverting amplifier. To control the gain and overcome previous problem and produce the precise gain required, the Wien bridge needs some form of automatic gain control, AGC. One popular method is shown here and uses a JFET transistor. This method can produce an excellent sinusoidal waveform that is stable. The key elements of the AGC circuit are highlighted in yellow. The JFET is placed in the negative feedback path. The gain of the op-amp is controlled by the components which include the JFET. The diode charges C3 to the negative peak of the signal. This develops the gate bias voltage for the JFET that is related to the output level. This is a classic negative feedback at work. When the R's and C's in the feedback circuit are equal, the frequency of the bridge is given by f of R is equal to 1/2 pi RC. Can you calculate what is the value of FR for the given Wien bridge? By using the given formula, just key in those values. And the value of FR is. Second example of RC feedback circuits is the phase shift oscillator. The basic circuit of an RC phase shift oscillator consists of an amplifier, 3 resistors and 3 capacitors connected in a feedback loop. The resistors and capacitors form a phase shift network which determines the frequency of oscillation. The amplifier amplifies the input signal and generates an output signal, which is then fed back into the input through the feedback loop. The circuit is designed to introduce a phase shift of 180 degrees between the input and output signals. For this reason, an inverting amplifier is required for the circuit. The attenuation, B, of the 3-section RC feedback circuit is B equals 1/29, where B equals R3/RF. Looking back at the circuit, to meet the greater than unity loop gain requirement, conditions for oscillation with the phase shift oscillator is that if all R's and C's are equal, the amplifier must have a gain of at least 29 to make up for the attenuation of the feedback circuit. This means that RF/R3 is greater or equal to 29. Under these conditions, the frequency of oscillation is given by equation. F of R is equal to 1/2 pi square root of 6 RC. In this example, you can try to run this oscillator circuit using multisim. Please take note, you can simulate the phase shift oscillator in multisim, but if there is a problem with starting the simulation, you can use combination of a switch and a DC voltage source as shown in circuit designed for next example. Now, let's try to design a phase shift oscillator with a frequency, FR, of 800 Hz and use capacitors with a value of 10 nanofarad. Remember, to design a complete circuit you need to find the value of R and RF first. Start by solving for the resistors needed in the feedback circuit. R is equal 8.12 kilo ohm. In this case we will choose a realistic value of R which is 8.2 kilo ohm. Then calculate the feedback resistor needed. R of F is 29 times of R, which is equal to 238 kilo ohm. Now we can complete the design as shown in the figure. In order to make this simulation workable in multisim, we need to add a switch and a DC voltage source as shown in next slide. By controlling switch S1, the simulation will work. From the virtual oscilloscope, the measured frequency is 791 Hz, which is close to the targeted frequency, FR, 800 Hz. The third and last example for RC feedback oscillators is the twin-T oscillator. The basic twin-T oscillator combines a low-pass and high-pass filter to form a notch filter at the oscillation frequency. An excellent notch filter can be formed by using Rs and Cs related by a factor of 2 as shown here. With this relationship, the oscillation frequency or f of R is approximately 1 over 2 pi RC. Although the RC feedback oscillators, particularly the Wien bridge, are generally suitable for frequencies up to about 1 MHz, LC feedback elements are normally used in oscillators that require higher frequencies of oscillation. It works on the principle of positive feedback, where a portion of the output signal is fed back into the input, causing the circuit to oscillate and generate a continuous waveform. The basic circuit of an LC feedback oscillator consists of an amplifier, an inductor and a capacitor connected in a feedback loop. The inductor stores energy in a magnetic field, while the capacitor stores energy in an electric field. The amplifier amplifies the input signal and generates an output signal, which is then fed back into the input through the feedback loop. The inductor and capacitor form the frequency-determining element of the circuit, which determines the frequency of the oscillation. A popular example of LC oscillator is the Colpitts oscillator. It uses two series capacitors in the resonant circuit. The feedback voltage or VF is developed across C1. The voltage developed across C2 is the oscillator's output voltage or Vout. The approximate frequency of oscillation is the resonant frequency of the LC circuit and is established by the values of C1, C2 and L, according to the formula f of R is equal to 1 over 2 pi and square root of LCT. As indicated in the figure, the input impedance or Zin of the amplifier acts as a load on the resonant feedback circuit and reduces the Q of the circuit, thus lowering the resonant frequency. As a rule of thumb, for a Q or quality factor greater than 10, this formula will give good result. Recall that CT or the total capacitance of two series capacitors is the product over sum of the individual capacitor. Therefore, f of R will be like this. When Q is less than 10, f of R is reduced significantly, and the previous formula need a correction for Q and again the f of R become like this. The Hartley oscillator is similar to the Colpitts oscillator, except the resonant circuit consists of two series inductors, or a single tapped inductor, and a parallel capacitor. The frequency for Q greater than 10 is like this. One advantage of a Hartley oscillator is that it can be tuned by using a variable capacitor in the resonant circuit. Next is the crystal oscillator. Crystal oscillators are highly stable oscillators for demanding circuits such as radio transmitters. Crystals have very high Q. Manufacturers prepare natural crystals, usually quartz, by mounting a very thin slab between metal electrodes. When a small AC voltage is applied, the crystal oscillates at its own resonant frequency. The crystal acts as the resonant circuit for the modified Colpitts oscillator and stabilizes the oscillations. The capacitors still tap off a feedback signal to the CE or common emitter amplifier. A relaxation oscillator is a type of electronic oscillator that generates a periodic waveform by charging and discharging a capacitor through a resistor. It works by using a circuit that alternately charges and discharges a capacitor through a resistor, creating an oscillating voltage across the capacitor. This voltage is then used to drive a switch, such as a transistor, which generates a periodic waveform at the output. It also used to generate triangular, sawtooth and square waveform. Relaxation oscillators are characterized by an RC timing circuit and a device that periodically changes state. A triangular wave oscillator for an example use 2 op-amps. For this circuit, the device that changes states is a comparator with hysteresis, Schmitt trigger. The RC timing device is an integrator. The operation is as follows. To begin, assume that the output voltage of the comparator is at its maximum negative level. This output is connected to the inverting input of the integrator through R1, producing a positive going ramp on the output of the integrator. When the ramp voltage reaches the upper trigger point, UTP, the comparator switches to its maximum positive level. This positive level causes the integrator ramp to change to a negative going direction. The ramp continues in this direction until the lower trigger point, LTP, of the comparator is reached. At this point, the comparator output switches back to the maximum negative level and the cycle repeats. The comparator output can be used as a square wave output. A square wave can be taken as an output here. This means this circuit can be used as both a triangular wave oscillator and square wave oscillator. The output amplitude of the square wave is set by the output swing of the comparator, and the resistors R2 and R3 set the amplitude of the triangular output by establishing the UTP and LTP voltages according to the following formulas, where the comparator output levels plus Vmax and Vmax are equal. The frequency of both waveforms depends on the R1 and C time constant, as well as the amplitude setting resistors, R2 and R3. By varying R1, the frequency of oscillation can be adjusted without changing the output amplitude. For the triangular wave generator, the frequency is found from the following formula. Now let's apply it to the following example. Can you calculate the frequency of the circuit shown here? By using the previously given formula, the f of R is equal to 671 Hz. Normally, the triangle wave generator uses fast comparators to avoid slew rate problems. For non-critical applications, a 741 will work nicely for low frequencies, less than 2 kHz. The circuit shown here is one you can construct easily in lab. The circuit is similar as previous example, but with a larger value of C. From this oscilloscope viewer, we can clearly measure and determine the amplitude of the triangular wave. A sawtooth VCO or voltage-controlled oscillator also uses an integrator to create the ramp portion of the waveform. In this case, when Vc greater than Vg plus 0.7 volt, the put switching devices fires and the capacitor discharges rapidly. In this circuit, the device that changes state is a PUT, and the RC timing circuit is an integrator. The frequency is shown as follows. Another relaxation oscillator that uses a Schmitt trigger is the basic square wave oscillator. The trigger points are set by R2 and R3. The capacitor charges and discharges between these following levels of VUTP and VLTP. And the period of the waveform is given by T is equal to 2R1C times ln of 1 plus 2R3 over R2. The 555 timer is a versatile integrated circuit that can be used as a timer, oscillator, and flip-flop. It is a highly stable device that can be used in a variety of applications, including oscillators. The basic circuit of a 555 timer oscillator consists of two comparators, a flip-flop, a discharge transistor, and a resistive voltage divider as shown in the figure. The 555 timer IC has three main terminals: the threshold terminal, the trigger terminal, and the discharge terminal. The resistor and capacitor are connected to these terminals to create the timing circuit. The operation of a 555 timer oscillator can be explained by the charging and discharging of the capacitor. When power is applied to the circuit, the capacitor charges through the resistor. When the voltage across the capacitor reaches a certain threshold, the 555 timer triggers and the capacitor discharges through the 555 timer. This process repeats itself, creating an oscillating voltage across the capacitor. This figure shown the operation of the 555 timer in the ostable mode oscillator. Now, CX begins charging through R1 and R2 as indicated in figure. When the capacitor voltage reaches 1/3 VCC, the lower comparator switches to its low output state, and when the capacitor voltage reaches 2/3 VCC, the upper comparator switches to its high output state. This resets the flip-flop, causes the base of QD to go high, and turns on the transistor. This sequence creates a discharge path for the capacitor through R2 and the transistor, as indicated. The capacitor now begins to discharge, causing the upper comparator to go low. At the point where the capacitor discharges down to 1/3 of VCC, the lower comparator switches high, setting the flip-flop, which makes the base of QD low and turns off the transistor. Another charging cycle begins, and the entire process repeats. The result is a rectangular wave output whose duty cycle depends on the values of R1 and R2. The frequency of the oscillation is determined by the time constant of the circuit, which is the product of the resistance and the capacitance. The frequency can be adjusted by changing the value of the resistor and/or capacitor. The frequency and duty cycle are given by and by selecting R1 and R2, The duty cycle of the output can be determined by using this formula. That's all for this chapter. We will meet again in the last chapter in the next video.